me. Yeah, C is for cookie, that's good enough for me. C is for cookie, that's good enough for me. Oh, cookie, cookie, cookie starts with C. Yeah! Cookie, cookie, cookie starts with C. Oh boy! Cookie, cookie, cookie starts with C.
Congratulations on completing chapters 1 to 6. This is the last day that is going to be covered as part of your mid-semester test. And what else starts with the letter C? Not just cookies, but chocolate. So we will again have some live demos and there will be chocolates for those participating. We have some more props today. It is Big Brain Day to solve some big brain problems. And we have some beautiful numbers here that we will use shortly. Today we are going to be talking about arrays. Arrays are the most basic data structure in C and allow us to contain sets of items. Arrays in C are unlike sets and lists in some other programming languages in that they can only contain one type of object. The type of the object is determined by the declaration of the type of the array when you declare it in C. An example might be, at its simplest, an array of numbers. In this case, we have simple integers, positive integers, including 0, going from 0 to 7. They are really important because up till this point, we've only been able to manipulate data that we're able to refer to directly in terms of a variable name. However, if we have a large set of data, if we've got a lot of items, we're not going to be able to create a new variable for each and every item. Further, we might not necessarily know at all times how many items we're getting in. So it becomes very important for us to build some kind of structure, some kind of abstraction, some way of talking about multiple different objects at once in the same setting and using just one single variable name. An array is a data type, just like an integer or a character. But it's also a data structure. It contains a way of storing and representing other types of information. So an array could contain ints, it could contain chars, it could contain even structs, which are other more complex data structures. An array is just the basic substrate that we're going to use to contain bounded sets, finite sets of items, where we know how many items we want to put in. An array might be considered to be somewhat of a boring data structure, but in reality, it's highly useful. Arrays are very, very powerful, and as you'll see in your first assignment, and maybe with a little preview on your mid-semester test, they enable us to do much of the data processing that one encounters in everyday life. One more tricky thing about arrays is that they're an abstraction. What they are is there's not actually, again, just like our other data types, there's not actually a set of specified boxes somewhere inside the computer. It's just a representation of a collection of ones and zeros. In this case, it's special syntax that we use to talk about a collection of different memory addresses. In this way, they can be thought of just a fancy syntax for pointers. Just like with pointer arithmetic, that we could point to a single location in memory and then ask what comes next and then ask what comes after that, we can do the same thing with arrays, just with slightly nicer syntax that allows us to forget about the fact that at the end of the day, we're manipulating ones and zeros and manipulating addresses. In this way, arrays are a form of syntactic sugar. What this means is that it's a fancy way of writing, perhaps much simpler and much more efficient and much more user-friendly, a simpler way of writing code that we already know how to write. There is nothing that you can do with an array that you can't do with pointers, but arrays make it much simpler and much easier to conceptualize what's going on. We have a few options in C for creating arrays. Firstly, we could allocate the memory that we need just for the array on the stack. We do this with a pair of square braces that are the suffix to the variable name. So we start with the type, then the variable name, and then we have our square braces to indicate that it's an array. When you declare an array like this, you must give it a fixed size. You must tell the compiler what is the maximum number of items that we're going to be putting in this array. In this case, we are putting 5 items in the array. Char, an array of 5 characters called A. We also could allocate and initialize the array. This means to populate the array if we already know what data we want in it. Taking our same syntax for our array of 5 characters, we could expand this syntax, but only when we create it. This is special creation and initialization syntax, by appending an equal sign and then using curly braces and telling the compiler the full set of elements that we want in this array. In this case, we are putting the string hello in there, and you'll notice an error on this slide. What is the error? Henny said it, but without the microphone, so we couldn't quite hear him. But the string hello has 6 letters in it, and we've only allocated room for 5. So this is a note for Liam to put down for me to correct my slide next time we get here. One other quirk of this form of initialization syntax is that you don't actually need that number 5 in there. This code would have been correct had we taken out the number 5 and just left the allocation on the other side. The compiler is smart enough to read the initialization and figure out how many items are there. One thing that's key to emphasize, though, is this syntax only works when we're creating the array. You can't refill the array with a new set of items by using this syntax. It's special for when you create it. Oh, and I can see Ashwin gave us, pointed out the error over there a minute ago before we even covered it in class. This is the problem with having the Zoom chat over there, is people can read my mind ahead of time. We can also use pointers to refer to the array. Remember, an array is just a location in memory, and so it has an address just like every other variable in C. If we have our array A that we declared previously, we can use a pointer to refer to it, but there's a little catch. Because an array is already referring to a chunk of memory, we don't need to use the ampersand to get the address of the array, because what the array is storing is actually an address. Arrays are just like pointers in this sense. It's just a fancy way of writing pointers. You'll notice here that I have made an integer pointer to A, and so this will also generate a complaint because there I have made a character array, and so it will complain that I've created an integer pointer to a character type. As we said before, if we take a look at what's actually happening in the memory, it's no different to our pointer structure. We still have the same units, the same chunks of memory, only now we have a new special variable A that uses a different syntax to pointers to point to the same address. And it points to the start of the chunk of memory where we are putting our string. In this way, there is a direct mapping between the syntax for the array, accessing the ith element like this, and accessing the ith element subsequent to a pointer's address using the syntax on the left-hand side. What gets passed if you pass an array to a function? What do you guys think happens? And Zoomies, hold off on the chat for a second, but you can raise your hand if you like, if you want to say the answer out loud. Or someone in the audience, what happens if you pass an array to a function?
Right. You said earlier that arrays are basically just address, so it would be similar to how you pass an address to a function. So the function can actually modify the array itself.
That's exactly what I was looking for. Just like when we pass a pointer in, we're able to manipulate and change the contents of the thing that the pointer points to. Because an array is just like a pointer, it's just an address. If we give a function the name of an array as input, the address of the array gets copied over in, and then we can manipulate the contents inside the function. Remember, though, that C is always passed by value. So it is the value of the address that's being copied over and not the contents of the array. Again, to repeat, this means if you change the contents of the array inside a function that's been passed the name of the array, you'll actually change the contents of the array in the calling function as well. But there is a limitation to this. Functions cannot return full arrays. This means if you declare an array inside of a function, you can't pass the whole array back. Why is this? Think back to our discussion about where variables get put when you create them. Let's say we create an array inside a function called FoA, and we want to pass that back to main. This is another question for our audience. What happens if I create this array in FoA and pass back the name FoA back to main? What happens to the memory that contained our array? And where's the microphone? Okay, haven't heard from you before. What's your name?
Dougal.
Dougal. Okay, so when we create our array inside the function foo, in which part of a computer's memory does it get placed?
The stack.
Yeah, it gets placed. Oh, this isn't on again. So Dougal, my friend here, his name is Dougal, and he said that when we create an array inside a function foo, it gets placed on the stack. And it gets placed in the stack frame belonging to what function?
Foo.
Foo, yeah. So what happens when foo returns the array?
The stack frame gets not, well, removed, or it becomes inaccessible?
Exactly, it becomes inaccessible or forgotten. Now, while we might get lucky and the array might still be there in memory, we're now using part of the memory on the stack that no longer belongs to us or belongs to our program. And so while it may work, that'd just be a lucky accident because we're no longer meant to have permission to access this variable. So if we pass the name of our array back to the main function, it's not going to work. Do you have an idea of how we might get around this limitation? Hold the microphone up.
Either we create the array before we call the function and pass the array as an argument to the function, or we allocate the array somewhere else in memory.
Thanks very much, Dougal. That was an excellent answer. So either we could use a lower stack frame, and we do that by making sure that we create the array in the calling function, or, as we will see in some later lectures, we have ways of actually directing the C compiler to create variables in different parts of the memory other than the stack. We now have a short array demo. This one's not live, this is just a code demo, but we'll get to our hands-on experiment shortly and our big brain. Here is quite a simple example of array manipulation. We have a hash-defined n5 over there, and we have declared an array over here, an integer array called A of size 5. Remember, a hash-define is basically just a find and replace that the preprocessor runs, the special part of the compiler. We then have a loop that goes through the array. The way it does this, starts at 0, goes up to n, and then we set each element of the array, so this is the syntax to set an element of an array, to the value of I, which is just our loop counter, times I plus 1 on 2. So we're doing a sum of a sequence. This little portion of code here, you're going to use over and over and over again. So pay attention now, but if you don't catch it now, there'll be plenty of opportunity to get some practice. This is just a loop to print out the entire contents of the array. This chunk of code, even though it's only 3 lines, would also make sense to potentially put in a function. Because many times when you're working with arrays, you are going to want to be able to print out and see the contents of them. So it is common practice to have a function called printArray that might take in a variable that specifies the size of the array, which tells the for loop how far to go, and then simply runs through the for loop and prints all the elements of the array. Let's give this a run. The usual error that I make. Our printing loop has gone ahead and printed using this syntax the ith element for each element I in the array. So this first %d refers to our loop index, and the second %d uses the syntax to get the ith element of the array. The only difference between setting and getting is you use it just like any other variable, but you specify the index to which you want to perform the operation, and then you either do a setting operation using the equal sign, or if you don't have the equal sign and just using like that, it's a getting operation. I've included in the slides a few different exercises for you to try at home. I encourage you to download these and at least do one of them before the upcoming mid-semester test. Because as we said, while the mid-semester test is going to focus on material from earlier in the semester, I'm guessing there's going to be at least one arrays question. So we have 3 different exercises for you to try, each with different basic array manipulation that will hone your skills in this syntax. Why are we bothering with arrays? Well, let's take the example of the Facebook news feed. Here is an example of the feed on both a phone and a computer. One common feature that the news feed has is that posts often appear chronologically, or at least semi-chronologically. So with each post, we're going to have an associated timestamp. That's a number that specifies when the post was created. If you're Facebook and you want to display these to the user in the order in which they were created, you're going to need to sort all of the posts. For that, you'll need some structure that can contain multiple different posts and multiple different timestamps. But let's, for the time being, just assume that we have only the timestamps in an array, and we're going to sort it that way, and after that, reconnect them back to the posts to which the timestamps are associated. And we're going to use some very simple timestamps. On the floor here, we have a few numbers from 0 to 8, and we'll use those for our demo. So we're going to do a little bit of sorting. So it's finally time for our big brain moment and for some audience volunteers to cover our sorting. So I will need 7 volunteers. Yash, I already promised you could be one. And Rosa, are you in here today? No, I can't see you. Promised you yesterday. Okay, Josh from the back. Who else? Was there a Joyce back there as well? Yes. And I'll need a few other volunteers whose names I don't know yet. Yes, what's your name? Say it louder. Ming. Okay, come down to the front. How many have I got so far? 4. I need 2 more. Fox, you up for it? Angel, have you been out to the front before? Okay, you're up. I think that's 3, 4, 5, 6, 7. 4, 5, 6, 7. Great. And I need a big brain person. Who is the big brain person? Come up. Remind me your name again? You'll have to say it when you get to the front. Okay, and I want all of my volunteers, each of you pick up a number, start in sequence. So, no, pick up the 6. Yeah, so Yash, you pick up the 5. And Joyce, pick up Angel, pick up the 2. Oh no, that's whatever. I can't see what number you're holding. 2. Okay, stand at the end. There you go, big brain. That goes on your head.
Okay.
Okay, you can put it on. I'm not going to force it on you. And we need a microphone. It fits on fairly snug.
I think so. It'll fall though.
Is it on? Okay, great. So everyone hold out your numbers nice and big because our Zoom audience is going to need to see these. And Fox, hold out your 0 right in front. You're wearing a black sweater, so it's a little hard to see. But Fox has a 0. Maybe hold it and cover your face with it. That'll be a little clearer. There we go. Okay, we can see all our numbers. And I didn't catch your name before. Arshia.
Yep.
Okay, hold your microphone pretty close to your mouth, otherwise people aren't going to be able to hear. Okay, so Arshia is our big brain for today, and she is going to help us with the task of sorting these numbers. So you are the director, and the rule is you're only allowed to direct one number at a time. So help me sort this array, timestamps of Facebook posts.
So wouldn't it just be in like order? So would it be 0 first and then?
So give us a set of instructions that we can use to put them in order.
So the one in the black hoodie. So 0 comes first in the line. So maybe you want to step up and then
Okay. Where do you want them to go?
in front of 8.
In front of 8. Okay, so here's another rule. You can only get people to swap. You can't just move people around. So Fox, come back.
Okay, so 0 can swap with 8. And then where's 1? Oh, there's no 1. Okay, so then 2 can swap with 7. 4 can swap with 6. And then 8 can swap with 6, yeah. And then 7 can swap with 8. Okay, I think that's done.
So what method did you use for figuring out who you were going to swap?
Ooh, just like the ascending order of numbers.
But how did you figure out what number, who to talk to next?
Based on the values of the high value.
So you went through and you looked for the highest value, or how were you doing it?
So I looked through the list, took the lowest value there, and then I placed it in the front, like in the second value or third value.
Okay. So how many times did you have to look through to find the lowest number?
Altogether, maybe
So
6 times?
we had to look through once for every number in the list. So we'll keep that in mind for later. Part of this process was going through over and over and over again, looking for the number that we wanted to swap, and then we had to make swaps. So let's go back again. Okay, and now I want you to do the same thing, but you have to use a different strategy. See if you can come up with another way of figuring out how to sort the list.
Okay, so then this time we'll swap 0 and 2. So we'll swap them together. And then we'll swap 4 and 2. And then, yeah, we're done.
And we are now reverse sorted. Let's swap that back again. Let's swap that back. The rule is it has to be in ascending order. But you have to use a different strategy. You can't just find the lowest number and then move it to the front.
Okay. Maybe.
Do you need a hint?
Yes.
Okay, so if we look at our first pair of numbers, are they in the right order?
No.
So what should we tell them to do?
Swap them.
Okay. There's your hint. See if you can.
We'll swap 8 and 6 as well. And then we'll swap 6 and 7 also again. And then
Okay, let's reverse that for a second. I'm going to add another rule for you. You've done very well so far, but now the rule is once you've started going through, you have to keep going further along. So we've swapped 8 and 7, and then, sorry, let's go back to the very start again so we can do that quickly again, because I lost track of it. So we swapped 8 and 7, we swapped 8 and 6, and assuming we can't go back, what's the next swap we make?
we swap 5 and 8.
Yep.
And then we swap 0 and 8. And then 4 and 8. And then 2 and 8. Wait,
Yep, we swapped 2 and 8. Very good.
But then they're not in order.
We're not in order. So how can we, is it more in order than it was before?
Yeah.
So can we make it, if we repeat that process again, do you think we'll get even more in order?
Yeah.
So let's try that.
Okay. So we again swap 7 and 6. And then 7 and 5. And then 7 and 0. And then 7 and 4. 7 and 2. 8 and 7.
Yep,
Eight and,
that's you too.
7 and then
Yeah, remind me your name again. Josh, sorry, I caught that before.
3.
Yeah. Okay, are we sorted?
No.
So what do we do?
I think I messed it up more than before. Do we just keep going?
Keep going.
Okay, so then 5 and 6. And then 6 and 0. And then 6 and 4. And then 6 and 2. And then 6 and 8. And then 6 and 7. So 6 and 8 swap first.
Yeah, 6 and 8.
and then 6 and 7 also swap.
Okay, so now let's start doing this a bit quicker. Can we fast forward?
Okay, so 5 and 0, 5 and 4, 5 and 2, 5 and 8, 5 and 7.
Wait. 5 and 8?
Oh, wait, why won't that happen?
So the problem here is we don't want to swap, we only want to swap numbers if it's getting us to a better place than before. So let's reset all the way back again and try this one more time. So this only works if at every time the swap that we make is improving how the array is. So let's swap U2. Is this a correct swap? Yes, 8's bigger, 8's bigger, 8's bigger, 8's bigger. Let's keep doing it. Okay, we've done our first run through. Now 7. Are you bigger? Bigger, 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 not bigger. Okay, let's do it again. Do you want to give the instructions?
Then 6 and 5, 6 and 0, 6 and 4, 6 and 2, and then 5 and 0, and then and then you have to stay there, right?
Yep, the 0 doesn't swap. So do we make another swap?
This order.
And now we're in sorted order. So can we have a big round of applause for all our volunteers? I think we've got chocolates for most of you, if not all of you, but if you missed out on a chocolate, come to me next lecture and we'll have some spare. And remind me your name again.
Arshia.
Arshia, okay. It might take me a try or two. Thank you very much. Thank you, Arshia Big Brain. And you can put your numbers back on the floor and we'll look at how to actually do this in code. And I think we might be a few chocolates short.
No, we've got enough.
We've got enough, just. So as everyone in the Zoom chat has noticed, this is in fact our last algorithm that we had over there was a representation of bubble sort. The first algorithm that we tried where we go along looking for the right number to put at the end was an algorithm called selection sort, for which I won't cover the code. But let's look at bubble sort first. And then we'll go to a slightly more advanced sort called insertion sort, which is a little bit better. Here is our bubble sort function. There are a few ingredients that make it work. The first ingredient, which is all important, is Arshia's swapping function. This is what allowed us to actually make the changes all the way along inside our array. Because arrays are just like pointers, it's okay that we've used pointers in this case, because what we're doing is we're swapping the contents of two different cells in our array, and those two different cells we can refer to by their memory addresses. If we scroll down, to our bubble sort function, you'll see that here we're going to actually take the addresses of some of our array elements, but we'll get to that in a moment. We have our inswap function, which was demonstrated by our volunteers at the end of last lecture, which involved having the 2 pointers in the temporary variable, and then you copied over one of the things to the temporary variable, you swapped the 2 items using pointers, and then you copied the temporary variable back to the one that you'd just overwritten. So that was our swapping function there. And then we have a main function. Here we have the same numbers in the same order that we had on the ground. So 8795024, exactly the same as we originally had there. Going to print the array before sorting. We'll sort it and then print it after. Now we get to the meat of the bubble sort function. This is how to implement in code the exact same procedure that we just did down here. We give as arguments to it our array and the size of the array. And one thing to note here is that even though our array is of size n, because we're in C, we start at 0, which means we can only go up to n-1, because if we're counting, if we have 7 items here, this is 0, 1, 2, 3, 4, 5, 6. There are 7 items, but the biggest index is n-1. So that's why our loop is only going to n-1. You'll notice in addition to that we're not using the greater than or equals to sign here. One big trap that you'll find when you're writing a lot of code and when you're implementing algorithms is off by one errors. These are things like forgetting that C arrays are indexed at 0, or confusing in this particular example whether you need to whether you're going all the way up to, say, the 6th one, and from the 6th one you're looking at the 7th, or if you're at the 7th one, and which is index number 6, and looking backwards. If we're looking forwards for a comparison, we're not going to want our array index our loop index to go all the way to the end, because at the end you have nothing to compare with further on with. So when you're writing your code, one thing to check very carefully is the bounds of your loops and the bounds of your array accesses to make sure that you're not accidentally going one too short or one too far. What we did when we were doing our bubble sort, what we were doing was going through step by step. We were going one run and we'd go do all the swaps we could make. Then we'd do another run and do all the swaps we could make. And we would do this one time for each of the elements, each of the elements in the array. The next part of bubble sort was to compare adjacent elements, and that's what we do in this loop. For every time we go through, we're going to compare adjacent elements and checking each time whether we need to make a swap. For each pair of elements, if we don't need to make the swap, we just move on. If we do need to make the swap, we do it and then move on. So we start J at the beginning. We go up to the second last element in this case, because we can't compare the last element with the element after the last element. And then we move on. At each element, and I'm going to adjust this code so I don't do the thing that I told you not to do. I'm going to add a paren there. There we go. At each element, check if the element you're at is bigger than the one after the one you're at. So this would be, for example, if we're at 4 and 5 is here, if 4 is bigger than 5, then make the swap. If it's not bigger than 5, don't make the swap. So let's muddle this up a bit again and do a comparison. So now I'm at 5 and I look at number 4. So let's say we're at J over here. J is pointing to the jth element. J is 0, 1, 2. J is 2. The jth element is 5. The jth plus 1 element is 4. 5 bigger than 4. Do we swap? Yes. And so we call our inswap function. And we know that each time, if we make at least one, if there's anything to do, we make the swap. And if there isn't anything to do, we're already sorted. And we do this once for every element in the array. And so we have a guarantee that by the end, our array is going to be sorted. Over here, we have our print array function, which is exactly what we talked about in our first array demo. We've made it a little simpler to see the contents of the array. Let's give this one a run. Before sorting, we have 8795024, and then 0245789. This question is a bit of a puzzler. Why might I want a different method of sorting other than this one? Liam, do we have the... Or let's take this from Zoom, perhaps. Is there someone on Zoom who wants to come on live, put your video on, and explain to the class why we might want another algorithm other than this one? Wada, do you have video? Do you want to come on and explain to people?
I think it is because this is fixed as well.
So we can see you on screen now. Explain to everyone why you think we might want other algorithms.
Because I think this may be critical because this involves two formulas, each of which iterates throughout the whole array. So maybe they can test it for difficulties for N squared, where N stands for the length of the array.
So what I think Wada is saying is that look at our loops. This loop always runs up to n minus 1, and this one assuming that each time that the maximum that this will run is n, it's going to run n times as well. It might run a little less, and then each of those times we're going to be making comparisons for each pair of elements. So for every time I go through, I'm going to look at every single pair. This seems pretty inefficient because if our array is already sorted, I'm still going to go through it again and again and again and again, making all the checks. So as written, there are already some really big problems with bubble sort. We can make these a little better by adding some catches for if things are going well. For example, if my array is already sorted. But it seems to be pretty inoptimal. We therefore look for other sorting algorithms, selection sort, which we've already seen, which is also not fantastic, but also insertion sort and then merge sort and quick sort are two fancy sorting algorithms, which we're really looking forward to, but are a little bit more complex. So we'll reserve for a better day when you don't have the mid-semester coming up and at the forefront of your minds. Let's take a look at insertion sort, our other sorting method for today. And then I will leave you in peace to study. In this sorting demo, we have a few auxiliary functions, extra functions that we're going to use to make our program a little more sophisticated, but that don't actually impact the sorting itself. One of the things we want to do in this program is allow the user to input the set of numbers that we want to be sorted. And we want them to allow them to enter in as many numbers as they like up to a reasonable limit, knowing that our computer is ultimately memory bounded. So we have our hash define. We're letting them write in a maximum of 10 values. And we're making an array that's big enough for that maximum of 10 values. Now, the user might choose to only enter 3, but by allocating 10, we have wasted a little space, but we've also guaranteed that we have enough room for the user to enter in all the numbers that the program permits. Some of you might ask, well, this seems inefficient. Surely there's a way in C to use only the memory that we need. There is, but it gets a little tricky because you have to consider things like, well, how much do I set aside at the beginning and how much do I set aside later? When do I add memory? C gives you the power to control these things manually, but because of all the complexities, it's an advanced topic, and we're just going to go ahead right now until we get to malloc in a few weeks and waste a little bit of space in return for making our lives easier ahead of time. Then we run a function readIntArray, and on the basis of what our program does, I'm going to assume that nnums gives us back the number of numbers that the user has entered up to a maximum of 10. We print the array, we sort the array, we print the array again, and we're done. Let's look at how we read in the values into the array. We have a nice print statement, enter as many numbers as you want, and then press Control-D to end. Remember, Control-D is our signal to the operating system that it should tell the program that no more input is coming. Scanf automatically realizes when it gets this signal from the operating system and terminates and doesn't return any more numbers. This loop allows us to detect that because scanf will only report back that it's read in a number so long as you haven't sent it that end signal, that end of file signal that you produce by pressing Control-D. If you think back a few lectures, we can also add input by pipes, and when a pipe or a redirect flag, one of the angle things, and when a file has finished being read, it also sends the end of file signal. So one way of doing it is press Control-D. The other way is just to feed in a file, and when the file ends, it automatically stops feeding things in. So while scanf successfully reads things in, check if we've already read in the maximum number of things that we're allowed to read. This is going to be 10, because if we go back up to the top, we can see in our main function. Where's our main function? There's our main function. The argument to readIntArray, the second argument is maxvals. So maxvals here, lowercase, is going to be 10. So if n is equal to 10, say that we have in excess of the number of variables that we're allowed to read in, and just increment a counter that counts how many we've gone over. Otherwise, if we haven't gone over, set the nth item of the array to this value next that we just read in via scanf. And then count the fact that we've read in another number. Print the number of values we've read in, which is n, because every time we read in another number successfully, we increment n, so print that out. And then if the user has typed in too many numbers, tell the user how many of the excess numbers there were, and just say that we've discarded them. We don't do anything with them. Print a new line, and then return back to the main function how many items were successfully read in. And I'm going to use my fancy VS Code ability to hide that, and we'll hide that, and we'll hide main for the minute, so we can focus on our sort int array. This is the core of insertion sort. This is our new sorting algorithm. It's better than in selection sort and better than bubble sort. And when we get to analysis of algorithms in another week or two, we will actually try and do the big O analysis to figure out what is the best case for these algorithms, what's the worst case for these algorithms, and what's the average case. Insertion sort works by going from the first element to the nth element. In this case, notice that it is strictly less than, which allows us to be sure that the maximum value that I is going to take inside the loop is n minus 1. So this gives us a hint that we are probably not going to be comparing from the end over past the end. So we're going to go once through each of these indices. I is going to take on each of those indices. And then for each of those, look, starting at I minus 1, go backwards. This gives us an idea that let's say we've gotten all the way to the end of that outer loop. J is going to be equal to the second last element in the array, and then J is going to go progressively down the line. If J were to be equal to 0, why would this be a problem for us? And we'll take this from the live audience. Liam, why don't we start I at 0? Sorry, my bad. Why don't we start I at 0? Got to say it into the mic so that the people on Zoom can hear.
Because you use z equals I minus 1, and if we set I initial I is 0, then 0 minus 1 will make an error.
So intuitively, what does that mean in terms of our array down there? So if we've set I to be equal to 0, that means we're at which element of the array?
It's the first element.
Yeah, the very first one. And if our comparison, which way is it looking? Are we looking to the larger element, the higher elements in the array, or the smaller elements?
Larger.
If you look at J is going to be comparing the prior element because we're setting J equal to I minus 1. So this would essentially be asking us to do a comparison from the 0th element of the array to the 0 minus 1th element of the array. No such element exists, and so we skip that and start I at 1. Thank you. Okay, Liam. Now that we know roughly how our program operates, we're going to set I to start at, we'll start it from this side here. We'll run all the way through the different I's and start at the end of the array because that'll help us get a sense of how the array is going to function. I'll swap these two numbers. Start at the end here for I, set J to be equal to the next number along, and then swap AI left into the correct position if we are not in the correct position. So it's asking us to do a comparison of these two numbers, the ith number and J, which is starting over here. Are these in the correct position already? Is 8 larger than 7? Great. Oh, these are too sorted. I need to muck this up a little more. There we go. Okay. 7 larger than 5. Oh, sorry, I should keep I the same. 8 larger than 7. Let's go back. This is I, this is J. Yep, we're good. Now what do I say to do to j? J goes down by 1. And so now 8 larger than 5. Swap. Do I swap? Do I swap? No, none of the swaps. So now let's look at what if, let's start it from the other end and see how this would work starting at the beginning. So we don't start with I here because this was the 0th one. If we start with I here, this becomes j, 4 bigger than 0. Yes, we're good. And now j can't go on anymore. J would hit the end, and so we give up on this one. We move I 1 over. Do it again. 2, 4. Finally, we have an I and a j that don't match. So we swap these, and now we move j 1 over. Is 4 bigger than 0? We're good. And so we don't need to make the swap, and we're done with this round. Oh, I dropped one of my microphones. If we repeat this process over and over and over and over, we're eventually going to get to the point where all the elements on one side of the array up to the value I are sorted. So we are progressively sorting larger and larger chunks of our array up until we get all the way to the end. And this is the intuition behind insertion sort, is that if you can make sure that the chunk that you've looked at thus far of your array is sorted, and you keep moving along the array, if at all times you're maintaining that the thing on one side of you is sorted and you've gone all the way to the end, you know that the whole thing is sorted. And this is the key intuition behind insertion sort. So unlike selection sort, where the intuition that we had was find the smallest number and move it into the right place, find the next smallest number and move it into the right place, and we know that once we've done that for every item in the array, we're in the correct place, the insertion sort intuition is a little different. These intuitions are also something that we talked about early on in loops called invariants. This is something that is always true, and we know that if with the invariant plus a little bit of progress, if we combine these two things, we can eventually reach an end condition that between the invariant and our statement about progress and our statement about where we've got to, we know for sure that our algorithm has succeeded. So for selection sort, it was the invariant was the next smallest item should already be moved into the furthest place. The thing that we did to make progress was go over each of the elements in the array, and our termination was already having seen all the elements in the array. Those three things together give us a proof that the array at the conclusion of selection sort was sorted. For each of the algorithms we're going to go through, we're going to want to make these proofs that have the starting condition, the thing that we're doing to make progress, the invariant, the ending condition, and then finally we combine those to make an argument for the fact that our algorithm works, and this is called a proof of correctness. That is all we've got for you today. Congratulations on making it through all the content up for the mid-semester test. I'll post some extra consultation hours for all of you, and have a wonderful weekend.